This is our Aromatic Reactions chapter, part 2. And the part 2 Zoom is going to cover Friedel crafts. If you learn nothing else this chapter, learn Friedel crafts. It's synthetically useful, one of the most synthetically useful experiments that you'll learn in organic chemistry. I'm assuming you've already watched the part 1 video that talked about electrophilic aromatic substitution, because the Friedel crafts follows that same mechanism. It is a version of an electrophilic aromatic substitution reaction. Just so special and so important that I thought it should just have its own Zoom video. Let's see. It's later than that. Looks like slide 14 or 15. Yeah, right there. Oh, maybe it does bear looking at that reaction mechanism again, just to remind you of it. No, not the Meisenheimer complex. We want the one with the sigma. Well, there we go. Sigma complex. The electrophilic aromatic substitution. Oh, that's not the general one though, right? Let's put the general one. There it is. You have an electrophile. Notice positive charge. It doesn't have to have a positive charge, I suppose, but if you're going to make a sigma complex, it would need to have one. So let's keep one with a positive charge, right? And then one of the pi bonds on the aromatic ring comes after that positive charge. And so connect the electrophile to your benzene ring and then form that sigma complex, which is an intermediate, not a transition state. It's an intermediate. And it's this resonance stabilized. That's what enables it to be around long enough to be a bona fide intermediate. On the positive charge, notice it goes ortho, para, and then ortho again. And you should know all these arrows, all the electron pushing arrows for that sigma complex. And then you have a second step, at least, where you do proton transfer to get rid of that hydrogen and restore the pi bond that you took out in this first step. The nucleophilic attack has a high activation energy, and the intermediate is higher in energy than the benzene ring was because it's no longer aromatic. So to restore the aromaticity and bring it down to lower energy versus the sigma complex, right? You need a base to take that proton off. Okay, so that was your quick review on the mechanism there in the sigma complex. Oops. Looks like slide 16. Let's do the slideshow mode. There'll be two versions of this, alkylation and acylation. We'll see what each of the two are. Both of them can eventually lead to an alkylated benzene ring. It's just the Friedel crafts alkylation kind of does it just in one step, so to speak. I mean, there's two steps, but you just need one set of reactants here. The acylation can be followed by a whole nother optional step called reduction, Clemmensen reduction, to turn that into an alkyl group having it attached. So this is synthetically useful because, right, the benzene ring is hard to do anything with. It's hard to break it down because it's so stable. And then doing an alkylation, it helps you to build onto that benzene ring. And this is one way to grow molecules, so to speak, to grow them, so to speak, right? To customize, to start with a benzene ring and then get some completely different molecule out in the end. And we'll see the reason why you want to have an alkylation versus when you want to use acylation followed by Clemmensen reduction to get to an alkylated benzene ring. So If you want to add an alkyl group, you would take an alkyl halide, and I suggest you keep chloride there. It doesn't have to be chloride, but chloride's the best one to use. In the presence of aluminum trichloride, you get 66% output of this. Now, notice how this attaches. And it might be a little tricky in that you might think that this proton is attaching to, or excuse me, this carbon is attaching to that carbon there because of the way this looks. If you were to just glance at this and not consider what's really happening, right? It kind of looks like this chain is that chain. It's not. That chain is this chain. And it's just visually. It's not just a matter like the chlorine comes off and you're done. Like you stick it here and take the chlorine off. No, the carbon is going to attach where the halogen used to be. So that carbon is this carbon. The attachment to the ring is going to happen at the carbon where the halogen leaves. That's very important if you want to get these questions correct and understand this, how this is going to work, when to use it and when not to use it. So the mechanism is going to be the same for the electrophilic aromatic substitution. In this first step, we are seeing what happens with our alkyl halide and the aluminum trichloride. The chloride is coming after the positively charged aluminum, right? That's a strong Lewis acid. It's really small and it has a +3 charge on the aluminum ion in there. So it's a Lewis acid. And notice we're going to attach the alkyl chloride to it, giving us tetrachloroaluminate. That's what you call this in the end after it detaches, right? And then the chlorine will detach from your alkyl halide, turning it into a carbocation with a positive charge where the chloride used to be attached. Whoops. So that carbon is that carbon is that carbon. This is what's going on behind the scenes in the reaction mechanism. And once you have the carbocation, then it's ready to do the electrophilic aromatic substitution step. This step precedes it. It gets it ready for it. It's what makes the carbocation. The carbocation is the electrophile. Right, just having an alkyl halide isn't necessarily an electrophile. It's an electrophile after you take the chloride off and you have a carbocation. So that's the electrophile. That's the electrophile that's going to get used here. The carbocation will be the electrophile that then runs through the rest of this process. So in the first step, we've made the carbocation. And then we can have it do the electrophilic aromatic substitution where the cation comes down here. It's the electrophile. Now, you don't call this electrophilic attack. They're still calling it nucleophilic attack but it's coming after the electrophile. It's just the way they call these things, right? And it attaches just like what you saw before. And that carbon, this one, just to kind of help you follow the carbon all the way through the mechanism. Form the sigma complex, know where the resonance arrows go, and then do a proton transfer in the end, right? This has a negative charge on this tetrachloroaluminate. So come pick up a proton and we'll detach it to make a pseudo HCl, right? That's a strong acid. It's not going to stay together. But this is OChem, and in OChem, they'll often show that in the molecular form, even though that's 100% ionized in solution. Just kind of gives them a way to account for where the electrons are. And then we'll reform the double bond inside of that ring so that we now have an aromatic system as opposed to just a sometimes conjugated diene. Right here, it's not conjugated, but in the other spaces. So, nucleophilic attack, proton transfer. Be careful which carbon you show connecting. Now, something should occur to you with regards to this mechanism because it's forming a carbocation. That carbocation is going to be as stable as it can be. If you had done this with the chlorine on the end, you would have tried to form a carbocation with a terminal positive charge, and that's not stable. That would have immediately rearranged to give you a secondary carbocation. And if this molecule happened to have the possibility of doing a carbocation rearrangement to form a tertiary, for example, if it had a methyl group right there, this species would have undergone carbocation rearrangement. Right, what the little hydrogen that was here, the hydride would have moved over one step and given you a carbocation rearrangement. Now, that doesn't mean that the aromatic substitution won't work. What it means is that this would now be in that location. And your product would be the benzene ring with an attachment at this carbon instead of that one. So in the original problem, it's attaching here. If it underwent a carbocation rearrangement, like if you had a methyl group there that would make it more stable, then it's going to attach at that location instead. Even though the halogen was initially attached over here at the blue carbon because of the carbocation rearrangement. Now, it's not like you can't do it intentionally to do that. You just have to be really aware. Why not just stick the chloride right there to begin with? When you're doing your starting molecules, if this is what you want in the end, you might as well start with something like that in the beginning and just have the chloride attached right there, as opposed to attaching it over here. So be on the lookout. Just, that can happen in the background if it can rearrange. The molecule they used in their example is not subject to a carbocation rearrangement because this location, it was perfectly symmetrical where it's secondary is the same as that location where it's secondary. And what you're not going to have it do is go primary. You don't go from the higher energy state to from the lower energy carbocation to an even higher one where it's on the end, where it's terminal. But here, even if it had moved over a carbon, it would have been the exact same molecule. They do that intentionally when they're writing these examples so that you don't get distracted by the complications. So you get the simple idea first and then consider complications to it. So here's one where we're showing that chloride right on the end. Yeah. And when it goes to form that carbocation, it's not going to be stabilized carbocation. It's going to immediately undergo carbocation rearrangement, the hydride shift, to put that positive charge in a more stable location. And so this is the site that would attach to the benzene ring. So if you had a benzene ring in this reaction, the benzene ring is going to attach at that carbon right there, not at the one where the halogen was. If we locate where the halogen is, the carbon where the halogen attached is there, but that's not where it's going to form your product. The product would be, there's the benzene ring, and then it'll have an attachment to this carbon. So you'll have a methyl group in one direction and an ethyl group in the other direction. The same product we had here, methyl group versus an ethyl group. But notice there they were starting with it in the terminal spot. And so it's not going to stay there, right? It just does a hydride shift. It does the carbocation rearrangement. And so you end up with the same product. And again, if this had a tertiary site on it, yeah, do 2 carbocation rearrangements. Do it twice. It would do it one time to pull that into the secondary. And if there was a tertiary, or it was being more stable, do it one more time. And then you're not going to get this product. You'd have methyls in 2 directions, but it's because I changed the molecule by adding a methyl group to give you like an even more stable situation. So be aware about the carbocation rearrangements in that. Now, here's one of the caveats. The carbon atom connected to the halogen has to be sp3 hybridized. So there's your one condition you've got to meet to be able to do this at all. That carbon that we've been trying to highlight for you has to be sp3. And then further, notice that polyalkylations can happen. So here you are, you're going to carry out this. We're already starting with a tertiary, so it can form that carbocation very easily. And it's not stopping at just one substitution. Notice it continued on and gave you another substitution. We'll learn in the next Zoom video why this went opposite as opposed to meta. It went para as opposed to meta. You could probably already imagine why it didn't immediately go ortho. And I'm not saying it won't go ortho, but that's not going to be a major product because look at how bulky that is. If they had used something like this, it's not bulky, well, then maybe it's also, in addition to going para, you would get somewhere it goes ortho. So you'd get multiple kinds of products out. How do you limit that? You just stoichiometrically limit how much reactant you have available. And we'll see in the next Zoom video when we're talking about adding multiple substituents onto the ring, what we mean by like controlling the reaction conditions. One control is don't have a lot of your terse butyl chloride around, limit it so that there's only enough to go around, like one per ring. And then we'll see, you know, some other features on that in the next Zoom video about when you're adding a secondary substituent. So that's the alkylation, and it gets you an alkyl attached to a benzene ring, right? Just kind of like right off the bat. Now, the question you should wonder about though is, what if you wanted that benzene ring to be attached? What if you wanted a product? Oops, maybe I shouldn't draw it there. What if the product that you want to get, let's see, 1, 2, 3, 4. 1, 2, 3, 4. What if you wanted the benzene ring to be attached? Oops, I lost the cursor because I'm up in the corner of the Zoom where the controls are. If you wanted the benzene ring attached to the straight chain alkane, is there anything that you could do? Sorry, I'm trying to get my iPad plugged in because the battery's getting low on it. It's always something. Always something every time I try to record Zoom. I think it's plugged in. I need to do some electrical work in my house and swap out that outlet because it's an old outlet. The plugs always want to fall out of it. If you wanted it to attach in that certain way at the terminal position, is there anything you could do to make it do that without having to worry about undergoing this carbocation rearrangement process? The answer is yes, but not a Friedel-Crafts alkylation. The answer is a Friedel-Crafts acylation, followed by a Clemmensen reduction. So followed by a whole second reaction step to happen. Just want to kind of show you the end result there. See here where you can end up with the benzene ring and have this attached where you can get the straight chain that's not branched, but you'll have to do what's called an acylation followed by a reduction. So let's see how the acylation works. Okay, here's our benzene ring. And we do have a halogen on there. And we're calling it an acyl group, right? And it's got a double bonded O and it produces a ketone. This is where you have two R's and a C double bond O in the middle of two R groups. That's a ketone. We'll see a lot of those in a later chapter. And this one we call acyl chloride. I don't know. Like there's no reason really behind that name. They just call it acyl chloride. And then we'll still have the aluminum trichloride around. Notice that the benzene ring is going to attach to the carbon where the chloride used to be attached. So the mechanism will look very similar to what you had before. This is the aromatic substitution, electrophilic aromatic substitution, meaning you have an electrophile in it. The first part up here to get to the acylium ion is describing what happens, right, between the acyl chloride you put in there and the aluminum trichloride. The chlorine comes after it and attaches, and then it detaches from the acyl chloride, leaving you with this resonance stabilized acylium ion. And notice there's a positive charge left behind on that carbon. That's the electrophilic site. So the Acylation ion is the actual electrophile that comes into play when you set it up like this. That chlorine comes off and attaches to the aluminum trichloride and leaves behind an Acylation ion. I'm a little bit distracted because I hear my doggie outside barking. She's not barking at the garbage collectors. It must be somebody walking a dog outside of our fence. So once we have the Acylation ion, right, the pi bond comes after that positive charge, nucleophilic attack, and then we have the sigma complex, just like we had before. You know, the other dog's barking with her, barking in solidarity. And then we'll do proton transfer. And we have this ketone. So let's see what we can do to this ketone to get that R group, to get a straight chain alkyl attached. Follow it by what's called a Clemmensen reduction. Reduction because it changes the oxidation state of that carbon. Here we have one. Put the acyl chloride group. Put this at the very end of the straight chain. In other words, don't attach it in the middle. Attach it at the end. That's the whole reason for going through all this process. If you want the benzene ring to attach in the middle, you don't need to do an acylation. Just do the alkylation and be done with it. It's when you need it attached to a straight chain that you need to go through this extra work. So we'll make a ketone out of it. This is a super, super handy reaction to know because once you have it as a ketone, there's a whole lot of other reactions you can subject this molecule to. Convert the ketone into an alcohol or convert the ketone into nitrile, right? You can change the oxygen out for nitrogen. We'll see that in another chapter. There's a lot of different reactions that you can do with ketones. We have a whole chapter devoted to aldehydes and ketones. So more to come. So don't forget about this acylation process. It's going to come in handy in the subsequent chapters as well, this part, and then we'll take this in another direction. But if we put it over catalyst, so this is like a solid zinc mercury alloy, solid zinc will work too. We'll have some acid. You need an acid around. You need a source of protons and then some heat. The overall result in the end, with a really high yield for organic chemistry, will be a straight chain. Now, take note of the difference between the straight chain and the acyl chloride, or maybe I should say the similarity between the straight chain and the acyl chloride. The carbon that attaches is the one where the oxygen used to be. So in this case, if we wanted to write this in the generic form of saying that that's right, got an R group on it. The R group, I'm going to color code that. The R group is this part, but that's not all that stays attached because it bonds, the benzene ring bonds to where the carbon for the carbonyl was. So you pick up this carbon also. So when you want to attach an R group, a particular R group, if you're going to do the Friedel-Crafts acylation followed by Clemmensen reduction, remember you're picking up a whole extra carbon in the process. Oops, I didn't want that one green. That one should be blue. So if you want 4 carbons, make sure that the R group only has 3 because the 4th carbon will be the carbon from the carbonyl. So you'll have questions that you'll have to ponder about. Start with a benzene ring and end with a straight chain attached. And you'll need to remember that when you draw the acyl chloride for that, the R group that you draw on the other side of the carbonyl needs to be one carbon less than what you wanted to attach, because the attachment will include the carbon from the carbonyl group. I hope that I'm making that clear, and it's so hard for me to know when I can't see your faces. What's going to attach will be the R group along with that carbon. Now, your book doesn't go into detail about what this Clemmensen reduction is like. It just says, you know, use these reagents and you'll get this product. And part of the reason they don't go into it is because the Clemmensen reduction process hasn't been fully agreed upon. They're still trying to figure out the details of what happens here. But I went through and looked online for what I could find about what is that mechanism. Now, I will not test you on the details of this Clemmensen reduction mechanism. This is the mechanism for the reduction step. See here, it's already formed the ketone. It's already formed this part. And I was interested in what's this mechanism. The chapter to me felt empty. I was left saying, well, wait a minute, how do you get to that step? And so you can see here's 3 different internet sources where I pulled up some graphics about how they think the mechanism might work. And actually these first 2 are similar, but not quite the same. They all start with the ketone form. So you've already done the acylation process and you have the ketone. They all use acid over, here's zinc and mercury. This one is acid over zinc mercury, but notice it's just showing it really interacting with the zinc. Down here, this source didn't even show really the zinc mercury, but they show the zinc part because that's the one that it's really going to be interacting with. So all of them have that same zinc catalyst going on. And they have a source of protons around. There's a source of protons. Here's some protons. There's some protons. Down here's protons. You need protons because you have to do a reduction. You have to reduce away that carbonyl group to end up with just 2 protons attached. So they all need a source of protons. In the first 2, the source of protons would be an acid. In this last one, it looks like the source of protons, was it this last one? No, it was, which one was it? I'm sorry. In this first one, they're also utilizing an alcohol as a source of protons. Right? There is a certain pKa associated with that acidic proton on an alcohol. So this might be a way to do it if you had something on your molecule that was very sensitive to reduction and you wanted to just do it in a softer way and use an alcohol for it instead. But let's see, what the first 2 do have something in common. You're protonating the oxygen. See how it's protonated there? And then down here also, it's protonated. We'll see this proton transfer from a ketone into an alcohol in a subsequent chapter. And we touched on it last semester in our chapter on alcohols, how to make an alcohol. Start with something called a ketone and protonate it. We'll see this again in our ketone aldehyde chapter. What are the reactions of ketones? One is interacting it with an acid to protonate it and make an alcohol. The bottom one doesn't do that step. The upper 2 postulated mechanisms do. These are like hypotheses for this. So they're protonating it first. And that leaves this carbonyl with a slightly positive charge. And the zinc is still, though, it's coming after it and attaching to the zinc. See the dashed line? It's absorbed. Oh, God. Adsorbed. Oh, my God. I've already been online for like 2 hours today and doing Zoom videos. And okay, I need the pen and I need that little dashed line. And down here they drew it as a solid, but they probably should have drawn it as a dashed line. It's adsorbed. Well, it's not like bonded, but it's what we call adsorbed. The electrons are attracted to that, and it loosens up what otherwise would have been some bonds. So you've got it adsorbed to the surface. And then we'll look along the first one and see what happens. Let me clear my marks out of the way. We'll lose water by having another source of protons around. And so you can see that down here. If you have more protons around, let's have one of the lone pairs. Right, this can happen in a couple ways. The lone pairs can come after it, and then you have loss of a leaving group. Whoever this source of this mechanism just shows the bond coming after the proton, but it would probably have been better if they had showed it in 2 steps, right? Where then it will look like this. And then followed by another step where you have loss of leaving group. Right, do a proton transfer to have this be H2O with a plus charge, and then do your loss of leaving group to pull it off. But they both just kind of shorthanded that. You know, when you're advanced in chemistry, then you can kind of do some of those shorthands that we don't let you do when you're first starting out. And then you'll notice it's attached, both of them, from the carbon, double bonded. Right, the water came off. And then this part is a little different. In the upper one, they have a source of alcohol around, and they use the alcohol as the source of the proton. So notice it was like a double bond adsorption turning into a single bond adsorption. That part's the same down here. What's different is the source of the proton. In this case, it's alcohol. In this case, it's still just acid. And both of them end up, though, with the proton attached. And then it comes after the second proton. I mean, could this be an alcohol here? Well, it could, but they're showing it just specifically as H+, meaning it's like hydrochloric acid. So here, it would come from here and go after the hydrogen, and then the hydrogen, those electrons that are right in that OH bond would go to the alcohol to make an ethoxy or ethoxide ion. Ethoxide, or I should say alkoxide in general. I'm just thinking, you know, if this is ethanol, right, you'd get ethoxide. Okay, so it's not quite time for wine. But I guess my brain is going down that route, and that's why it's thinking, you know, ethanol, time for ethanol, I need an ethanol break. And then in the end, you have hydrogens, 2 hydrogens attached, and no more oxygen attached. In the third possible mechanism, it's very different. We still have zinc, you know, coming after our molecule, but notice here, it's the double bond directly coming after it without a pre-protonation step. These ones had pre-protonation, this one doesn't. And so this step, this one is showing the oxygen attaching to the zinc. And notice it's got, I do believe that could be a small radical showing up right there. So see how it looks like it has an electron? Where is it coming from? Well, notice there's a little attachment right here. So you have 2 electrons coming here, but maybe 1 electron coming up and depositing on that carbon. And then they're just saying, okay, well, let's take zinc oxide away, meaning leave the oxygen behind. And then it just kind of skips over to this step, and somehow this is double bonded, right? That electron will form 1 bond, and then you'll get those 2 electrons forming another bond where it's adsorbed. And then do the protonation. So that's like this step here. From this point on, it's the same. What was different about it was how it started. So this is, this is how scientists, how they do the science. They think, well, how might the mechanism work? And they do tests in the laboratories to see, well, what's attached and where is it attached? And use spectroscopy to explore that, or isotopically label what's going on and explore it that way. Time resolved spectroscopy. So this is an ongoing research. And this is all we need to say about Friedel crafts, other than one more time. Learn the Friedel crafts. I won't ask you the details on the Clemenson part of the mechanism. Let's see, the next slide is substituent effects. You'll just need to know that when you go from this, use these reagents to get to this product. And then, right, you'll need to know this part of the mechanism for each of these. You need to be able to draw and to recognize the sigma complexes for all these different forms. They're all the same, with the substituent on there, and then for every one of these sigma complexes, regardless of the reaction it came out of, they're all the exact same pattern. So if you learn it well once, all the rest are the exact same pattern. Okay, learn the Friedel crafts.